Sweet. So today's problem is linked list cycle detection. Definitely a classic, like y'all said in chat. Pretty easy algorithm actually. We'll just kind of talk through a naive way to handle this and then a very easy way to optimize it. So let's go ahead and read the problem prompt. It says, given the beginning of a linked list head, we want to return true if there is a cycle in the linked list, and otherwise we want to return false. And then they clarify that there is a cycle in a linked list if at least one node in the list can be visited again by following that next pointer. And internally, index determines the index of the beginning of the cycle if it exists. The tail node of the list will set its next pointer to the indexed node, so to speak. And if index equals -1, then the tail node points to null and no cycle exists. So this is just a very fancy way of saying like what a cycle looks like is the quote-unquote last node pointing back to somewhere else in the list rather than just pointing to nothing. We don't need index as far as I know for this problem, so and we don't need to find it. They're just saying, hey, here's one way we could define cycle more rigorously is if we said, hey, a cycle would be if this guy pointed to index 1, and that would create a cycle. And if it points to index -1, then that means it just points to nothing, which means that there isn't a cycle. So I'm not really sure why they include that, but that's what they're trying to say there. Okay, so we can tell very easily visually from this that there's a cycle because, oh look, there's a node that's pointing at a node that we've already visited. So this is more to their definition up here that says there's a cycle if at least one node in the list can be visited again by following the next pointer. So in this case, if we just follow these arrows, we get to 4 and we go back to a node that we've already seen, right? So yeah, in this case, we would return true. They do some information about the indexing here, but again, that's not really of interest to us. The next one will return false because this one has no cycles. If we were to follow the next pointer here, it would point to nothing. So if we just continue to follow the next pointers, we're never going to get back to a node that we've seen before. Okay, some constraints. They give us that the length of the list will be between 1 and 1,000. The individual values are between -1,000 and +1,000. Again, we don't really care about that. And then they explain it this way. They say either the index is -1 or a valid index in the linked list. And this just means either there's no cycle or the cycle points back to somewhere in the list, which, again, not really 100% sure why they need to give us that information. Okay, so let's talk about a naive way to do this, and I don't even know if we need to diagram this one kind of for the first time here. The way that we would have done this historically, so using the knowledge that we've had from like previous problems, we've always wanted to say, hey, if there's duplicates, or if we want to detect duplicates, then we can just use a set, right? So a really straightforward way to do this that doesn't require any knowledge of linked list algorithms, we could say, like, let's make a node set that is empty at first, and then we can say, let's go ahead and have like a current pointer that points originally at the head. And then as long as current is pointing at a node at all, what will we do? We'll go ahead and add the node to node set. Okay, and then move current on to the next position. Okay, and if eventually, so this is just what do we need to do to get to the next node. The next thing we need to check is, hey, have we seen this node before? So if current is in the node set, in that case, we fail immediately. We literally, by definition, have encountered a cycle because they said a cycle occurs if we follow the next pointer and eventually we see a node again, right? So this would definitely prompt us to return false immediately. And if there is no cycle, then we'll just get through this and eventually we'll fail on this condition. We'll hit whatever's after the last node, which will be none. And if that happens, then we successfully got all the way through instead of infinite cycling, and we can just return true. So this is a very straightforward, oh, guys, what did I do wrong? I literally was like, this is the easiest possible way to do this. Hello? Oh, just kidding. I just have the I just have the reasoning backwards. We return true if we detect a cycle, and we return false if we do not detect a cycle. Embarrassing. Okay, anyways, definitely works. We can go ahead and submit just to confirm it works in general. Now, what's the weakness of this? Well, we need to use O of n space in this case. That's like roughly true here. So in the worst case, we might need to get through the entire list before realizing at the very end, oh, there's a cycle. And we have to store, in this case, the pointers for each of these objects in like a separate data structure. So we'd like to be able to do this without needing to use extra space, although this is fairly quick. As soon as we hit the cycle, we detect it immediately. So, you know, from an interview perspective, this isn't necessarily a bad answer. It's just it requires extra space, but it runs pretty quick, which we like, right? Okay, so what's the alternative here? Let's actually do a little diagramming for the optimized solution. So I'll go ahead and say we'll do an example with a cycle here. So we've got something like this. Doesn't really matter what the values are here. But let's say we got 0, 1, 2. Man, that's not a circle. And then maybe we'll put the cycle right here after this one. We'll have it just point right on back here. Okay, so pretty commonly known algorithm here that is often called either fast pointer, slow pointer, or sometimes tortoise and hare. And that's exactly what it sounds like. We're basically going to have two pointers. One of them is going to go, and technically this is arbitrary, but this is a really common way to implement it. One of them is going to go one node at a time, and one of them is going to go two nodes at a time. Okay, and it doesn't, you don't have to do those exact numbers. It is probably the most common just because it's very easy to figure out what's happening. But I think, in my brain I've been saying this to myself, but I don't actually know if this is true. I think they just need to be mutually prime, which means eventually... No, actually they could be anything, huh? Wait, let me think about this. I think they just need to be mutually prime so that there's a guarantee that they hit each other eventually, which we'll talk about literally right now. So here's what we'll do. We'll have red be our slow pointer. We'll have blue be our fast pointer. And the way the algorithm works is slow moves once along the next, and fast moves twice. Now, if there was no cycle here, so we'll just keep doing that. If there's no cycle, eventually fast just gets to the end, and ta-da, we're done. So that's definitely one way this can turn out. Now, if there is a cycle and we continue this, what'll happen, slow moves over once, fast moves over twice, and eventually the guarantee of this algorithm is that these two, if there is a cycle, will end up in the same place. And there's lots of reasons for that, but in short, however many nodes are here, eventually we have to be in such a position that like basically the modulus 1 is the same as the modulus 2. So it doesn't really matter when that happens, but if there is a cycle, we're guaranteed that that'll happen eventually. So yeah, that's kind of it, actually. There's not much else to say here. So if there is a cycle, eventually slow and fast will be in the same place. If there's not a cycle, we'll detect that as well, because fast will just hit like a none node. And if it didn't hit a none node, then we would know that eventually it has to cycle back around and hit slow. Yeah, I kind of want to do like more rigorous analysis on that, because I think what I said about the modulus might not be 100% correct. But in short, definitely works. I guess another way to think about this is that the distance, so if we just circle back for a second here, when we start this, the distance is 1, right? When we do one more step, so I should say when we enter, when both nodes have entered the cycle, the distance is 1. When we move over again, the distance between them is, you can think of it as 2 from fast to slow. And then when we do it one more time, the distance between them is 0. So I guess it's actually more, what, It just eventually we have to like run through the entire sequence of possible distances, and eventually we get to 0 because the distance for each individual step is 1. Like we reduce that distance by 1. I guess we increase it depending on how you measure it. Anyways, eventually it circles back to 0 and we're done. If there's a cycle, they're in the same place. We confirm that there truly is a cycle and we're done. And notice the only thing we needed to use as far as extra space goes is just the slow pointer and the fast pointer. So we don't have to store the nodes anywhere. We just let them run through and eventually they hit each other, or eventually the fast gets to none. All right, let's code it out and that'll be it for tonight. Pretty light session, but pretty important algorithm to know. Okay, so let's do this with no additional space used, or just the 2 pointers of additional space. We can say slow and fast are both going to be head. So actually one thing we can do is we can write it like this. So slow and fast will both start at the head. We can say, let me think about this. So we want to move, like the end condition here, assuming that there is no cycle, is we want for fast to be at the end of the list. So what are the different ways that can turn out? We could say, is it just like while not? While fast? Is that sufficient? Let's think about this. If there's an odd number of nodes, then this isn't going to be great, because when we get to the last part, we're going to try and do fast.next.next, and it's going to go, oh, we can't do that because... Yeah, exactly. So, yeah. So in chat, someone said, fantastically, we're going to move fast twice, so we also want to check fast.next. So if we have an odd number of nodes, what'll happen here is fast will start at 1, and then it'll go to 3, and then it'll go to 5, right? And at this point, it'll still be valid, but we'll try and do fast.next.next. Well, here's the problem. Fast.next is none, and none does not have a next pointer, right? So not only do we need to check that we have a node that we're currently looking at, we also need to make sure that there's actually a next node following it, so we can say fast and fast.next. So if either of these is none, so either we're here and there's nothing after it, or... So if there's an even number of nodes, then we'll start here, we'll go here, we'll go to like none right here. And at this point, there just will not be a fast pointer at all, right? Or it'll be pointing to nothing. So this captures both scenarios. Either we hit the none node or we hit the thing right before the none node. Both of those like will tell us, hey, we reached the end of the list, which wouldn't happen if we had a cycle, right? Okay, so while fast and also fast.next, I need a colon there. What are we going to do? Slow is going to move over 1. Fast is going to move over twice. Okay, and then how do we detect a cycle? Well, do we check it ahead of time or afterwards? Well, we definitely don't want to check it ahead of time, because if we do that, then it's just going to always return whatever we put here. So we'll move them over and then we'll check, hey, is slow the same as fast? If so, there's a cycle, we can return true. And if we get all the way through this and we eventually hit this condition where there's an end of list that we detect, we can return false. Ooh, someone's typing. What did I mess up? Or are you just preparing to be like, hell yeah, we did it? Ooh, I checked them first in my first solution. Ooh. Oh, yeah. And the problem with that, it's like in terms of do we check at the beginning or the end of the loop? Well, if we check it at the beginning, we initialized these both to head. Of course, it's going to return true in this case, right? So we put it at the end to say, okay, after we move it, do we have them at the same place? Okay, if they are at the same place, there was a cycle and we can return true. Otherwise, we get all the way to the end and they never hit each other, and the fast pointer is at the end of the list, so we can return false for no cycle. Did it work? Oh, thank God. Very often I mess up these like very simple problems like horrendously, so I'm glad this one worked out. I'm really glad this one worked out. And again, this is what we can refer to as fast pointer, slow pointer, or tortoise and hare as an algorithm. And the whole way it works is every time we move over fast twice and slow once, we increase the distance by 1 until eventually we wrap around and the distance is 0 if there is a cycle. And yeah, that's that. Can you do my coding assessment sitting in my mailbox? You're cooked, I'm sorry. Just kidding, you're not cooked. You're gonna do great. And I can't wait to hear about your employment opportunity that you get from completing that coding assessment. But thanks for tuning in, guys. This has been linked list cycle detection, and we're back tomorrow for reorder list. This is kind of a crazy problem, actually. It combines a previous problem we've looked at. It's going to be real fun. See you tomorrow for that, but have a good night. Also, if you have any questions, let me know. I'll be around.